So for Unit 5, we're going to be focused on this single large notebook that looks and tackles this prostate cancer grade assessment challenge in Kaggle. So this challenge. You should join the challenge so that you can edit this notebook and work on it. I'll provide a link. I made this notebook public, and then what you want to do is make a copy of this. So to make a copy of it, this uses the Git hub, the Git terminology of a fork of the stuff. So you should be able to go up here and say copy and edit the kernel. It'll create a fork of this kernel and make a copy of it in your area so that you can modify it. And then once you do, like here, I'm just going to go in and edit this kernel. By default, it may be using GPUs, and you should say, okay, we are set up to use those. Now, you have limited time on GPUs and what are called TPUs here. So you can turn on the GPU there, and like I've used 10 hours of GPU time this week, and I have 30 hours total, so you probably won't run into any trouble with that, either with GPUs or TPUs. So we'll talk about that, and that'll be something to see. But when you run this notebook, you probably want to make sure that GPUs is turned on. It makes running or certain things much faster. Although if you're doing lots of slow editing and stuff, you can just run it on a CPU initially. Because it's the Kaggle notebook and using competition, you want to turn internet off. It should be off on this notebook. Okay, so here's an overview of this notebook. Again, we're going through this challenge here. We have a link to that. A good thing to look at is some of the top notebooks out there. Here's this notebook that's available. It's top loaded notebook out there. And it goes over this domain. What is prostate cancer? How is it graded? Where does this data come from? What is called the Gleason score, and what is the ISIP score here that we're going to use? And how is this kind of generated? Then it shows some samples of cancer, and it shows some samples, loads the data, and then shows some sample images. One thing we'll see is that what we typically see is a colon is a long string. So the test image and the region is spread out, and there's a lot of white space around this, and we'll talk a little more about this later for this. But that's the idea of these images, and then they're scored usually between 0 and 5 here. Okay, and then there's more stuff, but I'm not going to go into anything more with this basic image file. This notebook I'm using actually based on this other notebook file here that I have linked to also. So typical notebook, so we can run, we import all of our libraries we're going to use here for this. We also set up some stuff for the TPUs. So this configuration stuff here detects if we're working with a TPU or a GPU and how it works, and we create what is called a strategy variable here, and then when we run our notebook, we run it within our strategy. And again, depending on what we set up over here, it should detect the right version of this. And in fact, I'm going to have you do a little research on these and include that in as your first write-up question for this. Okay, so we detect that. Oopsie. Okay, sometimes I have some problems with this, and so I had to restart this session. I just hit restart session here and then re-imported the libraries again. And again, what you should get is what are called the number of replicas or instances or processors running in, because we don't have TPUs selected. There's one GPU running. Otherwise, if you're running TPUs, you might get 8 separate processors running here. So okay, now we're going to import our Okay, yes, so we've imported we've decided to find some variables here, also some paths for where our data is being stored. We have training and test data available, and we read in our test data there's 10,616 images in our test database for this. Right now there's no real test data available, but it's only available when you actually submit your notebook. So there's just a couple sample test names here for this, but no test images. There's some pre-processing, and again, I'm not going to go over again, every data set is a little different here, and so this data is in TIFF in a special format that's used often in medical for medical images, and so this does some processing of that and brings in those images. We're going to then try to this routine will import all these images using this pre-process routine and import it. Now, one thing to note is that this takes a long time to run. You can see each image is importing here. So rather than just doing all 10,000 images initially, right now we have this set to only do 500 images. So this will actually quit after 500 images. Here, there's this little code here that'll break out of this loop after that time. But when you're really using this data, you should uncomment this line of code and comment out that line of code so that you're using the full data set. What this does is look at the shape, the size of the number of images we already have, the 10,600, and use that here. So later on, once you get this kind of working or set, you want to do a full run, you should set that up. But for this again, so once this gets to 500 images, it should stop for us. Okay, so now we've got our images run. There's a little routine that you can stick in here that'll time these cells. So sometimes when these cells are running a long time, we have that set up so we can kind of see. So again, now we only have 500 images. They're 24 by 24 pixels. They've been resized in 3 colors. And then our output is 6 cells, 500 for all 500 units. And again, we're predicting the score is either 0, 1, 2, 3, 4, 5 is the score we're predicting on these. We're going to break the data into some test and some training, some validation stuff and some training data. And then we're going to look at some image augmentation options here. And again, later on, you can come back and look at this. Now, this is using some TensorFlow libraries that are a little different than we've used before, but there's different methods for manipulating this data, these images in TensorFlow, and this can be done rather quickly with some of the TensorFlow things, especially if we have the TensorFlow accelerator set up here. So, but right now we're not doing any of these here. We are setting up these training sets here, and so we're using some of the TensorFlow libraries to get this training data, map it up, and set it up into batch sizes, and same with our validation data here. And now we'll create our models for this. So we're going to define a couple functions here. So rather than creating our model directly, we're going to make some functions that will create different kinds of models that we can swap. So we're going to define our input and our output sizes here. And like here's a custom, just build a custom model. So we're just going to do sequential. We're going to lay out the layers here. And then here's our final output layer. And then we're going to return that model called NN here. So this is we can call this later on to create our neural network model. But if we want to do a different model, so we want to use a pre-built or predefined VGG model. Here's this build model VGG where we have that set up. And when we can pass in some weight settings here, and we can actually load in the weights here. And so we're going to create a pre-trained model. We're then going to use sequential to use that pre-trained model and add a global average pooling on top of that, add an output layer. We could also add some more dense layers on top of that if we want. And then we're going to print out a summary of the model and return it. So in this case, Up here our model was called NN for neural networks. Here the model that we're creating is called model, and we're returning that. So each case we're going to return model. Here's another one that creates an exception model. Here this is a pre-built model, and we're bringing in pre-built weights for this and setting it up very similar to before. And this was the method that was originally in this notebook. Was a DenseNet pre-built model. So we can bring that in, and we can bring in this weights for this DenseNet system, and set up the model, use sequential, and add these routines to this model. So some of these are using pre-trained models. This first one isn't, but the other three are all using pre-trained models. Now we've been skipping the textbook now, but let's jump back to the textbook and talk a little bit about this. So your textbook, we're going to jump back to chapter 10 where we left off there. And one of the things we're going to do is talk about building more complex models using this functional API. And we'll get to that in just a sec. But chapter 11 of the text has a whole section on reusing pre-trained layers, and one of the advantages of this is what is called transfer learning. So we might train a large network with one data set, and then we'll reuse this in our thing. So we have some initial weights set up here. So you should read through this section. It talks about taking this network here and then taking a whole section of it and reusing it here. And we typically have to redo the top part of the network where we're doing our outputs and maybe final dense layers or stuff, but the rest of the layer is hidden. This is again done before we went to the CNNs, where we're actually using these a lot, but this is kind of the idea here. And again, it walks you through this whole transfer learning with Keras and how to load models in and set them up and stuff like that. And that's basically what we're doing here. Again, we're loading in a pre-trained model. We're saying do not include the top, and then we're adding on the top layers onto this pre-trained model for this. Again, here's another model, and here's another way of doing that. Now, with some of the more complex models, we can't just use this sequential model. The sequential model, each layer is just put and connected one layer right on top of the other. I don't know if earlier we mentioned this Inception model where we have a layer and it actually branches out and is used for input to a lot of different convolutional layers that's fed up, and then those are merged together here. And so each layer is not just connected to sequentially to the layer below it. So if we're going to create a model like this, we have to use what is called the functional API for this. And again, if we go back to your book, chapter 10, back on chapter 10, they have a whole section on building these complex models using this functional API. They look at this wide and deep model again, where we have inputs going through, and then they're taking the part of this input layer and also jumping it up. So then they're using this concatenation layer to combine inputs from two different layers and feed that onwards. And we're not actually going to use this this wide and narrow one, because now that we're into convolutional neural networks, our networks are even more complicated. But this, you can see this whole thing where we're sending inputs to different places, and here we're using a concatenation of all these different values together and stuff. So this code here shows us how to do that. Somewhat it can seem rather complicated at first. So we define layers. Again, we can say like a convolutional 2D layer or a maxed pooling 2D layer here. We specify the strides and the pool size and stuff like that. We can also give these layers names so that when we do a printout, the names will be shown in the printouts. These are just internal names here, but we also save these layers as variables. So here's the labels, and I generally use the same variable name and the name here so that they're easier to follow. But then when we create one layer and connect one, each time we create a layer, we have to say where it's getting the inputs. So it's not just sequential. So then we say this pre-processing layer 1. Since that's the name here, we're going to use that here. So here's where we define our layer, and then we add another parameter onto this is where it's getting its inputs. And so for building something like this, where like a bunch of these layers get access from this pre-processing layer here, we'll see that here. So here's a convolution 1 by 1 layer, another 1 by 1 layer, and both of these are getting inputs from this pre-processing layer 2 here. In fact, there are four different pre-processing or areas that get that. These 4 cells all get this pre-processing layer here, so this input is used there. And then some of these, like this 3 by 3 convolutional layer, is actually getting its input from that area. So we'll see that's listed here as the input. So you can connect, it's kind of like Lego blocks, you can connect, or stringing things together, you can connect any layer to any other layer this way. And then finally we will concatenate. There's this new concatenation layer, and we'll specify the all the different layers we're concatenating together to get this one layer. So this is just one of these Inception modules up here, and we're going to use those multiple times here to set this up, and then we're going to feed through. So again, this just shows an example of using this functional API to do more complicated layer structures, and you can try out different layer structures, but I thought this would be a good example to show that and tie it into this textbook example. Okay, once we define these networks, we will then call them when we build our model. We'll call one of these different methods above. We have to do this within this scope strategy. We defined this earlier. The strategy was tied to whether or not we're using a GPU or CPU, and so inside Keras or TensorFlow here, we need to define this strategy so that, and again, I'm not going to go into details what that is, but it just allows us to work within the GPU framework or the TPU framework for that. Okay, so we're going to define our model, and then we're going to compile our model. And one thing we're going to specify is an optimizer for our model here. And before we were just specifying an optimizer directly here, but now we're often going to define a variable up here and use that variable for this. So maybe I'll use this RMS prop optimizer. So I'm just going to switch this around here and plug in the optimizer here. Or if I want to use an atom optimizer, I could also plug that in. So what are these optimizers, you might ask? So I'm going to have you do a little research on this, but it really ties into our textbook around page 355. So let's look there. So back to chapter 11 of our textbook, it talks about these learning optimizers and kind of the idea of momentum. And again, we're not going to go over too much of the math here and the initial ones, but the idea is that if you were in some, imagine you have all these weights you're changing, and so you're in an n-dimensional space with where each weight is a separate a dimension you can change. The question is, which weights do you change? And kind of look at that is, which way do you want to step? Do you want to change these weights or positive, negative, or what? And you kind of know where you want to go, or possibly, and so you figure out how much weight you want to change as you make these steps, and you do these incremental changes. You don't want to change things too fast, because again, different images will contribute and want to make different changes to your weights. You want to do this, and so this talks about optimal ways, or ways to try to adjust these, and how it's developed over time in different ways. Two that are again used frequently today are RMS prop, which improves on the Atagrad version of the algorithm, and again, you can read how this works, but it's again trying to find the global optimum without overshooting. Sometimes these methods, they'll change the weights so quickly that they'll overshoot, and then they'll change them back and overshoot, and they keep overshooting on these. And so how do we change that so we don't overshoot but yet get to the answer quickly? Another one is this atom optimizer, which again is built off of an adjustment off RMS prop and an improvement supposedly on that. And so these are the two we'll be looking at. And so in your stuff we have RMS, prop, and atom. And in fact, you can actually click on this and look at some details in the Keras documentation on these optimizers too. But within these optimizers, you can also specify an initial learning rate and some other parameters here. I'm not going to go into too much detail, but I'm going to let you read a little bit about these and then eventually choose one of these optimizers to use in your code here. Okay. Another thing we've touched on briefly is callbacks, but now we find this in our textbook back in chapter 10. So chapter 10 has a whole section on using callbacks. When we're training our method with the fit method, we can define certain callbacks. So as it's going through the training, it will call these methods periodically so we can update and adjust our training as we go. A couple common ones we're going to do. One is to reduce the learning rate here. So if our learning is improving, we can reduce the learning rate. So we can specify patience, how long we wait before we reduce the learning rate, what we're going to monitor to determine this, and then how much to reduce the learning rate as we go. So that's a common one. Early stopping. It's hard to know how long to train these networks, so again we can set this up so that if, in this case, valuation loss, if that is not changed at all, we're going to just stop our network here. We can also do what is called some saving model checkpoints. We can periodically save all of our weights, and in fact we can set this up so it only saves the best weight. So only if things are improving, each model if it improves, we'll save those weights. And we can actually specify here where we're specifying how many epochs we're training and the current accuracy of that model. So as we're going through and we're running through an epoch and it's good accuracy, this will automatically change that stuff. So you again read up a little bit about these callbacks, and again we can use these callbacks when we're setting. So when we're specifying where our fit function, we can specify what callbacks we want to use here in this little array. Okay, I skipped over one other thing. That was usually we train our model, and after we train our model, we'll then plot a graph of how training went. But sometimes it's nice to be able to monitor this as you're going along. And there's something called Tensor board for visualization that's built into TensorFlow and used. And in fact, it's described in your textbook also right above these callbacks. I'm sorry, right after the callbacks. So it talks about Tensor board and setting that up, and then you can open up a browser window and show as your model is being trained. And this is particularly useful as if your model trains over hours and hours or days to monitor it and how it works. In order for this to work, you have to tie TensorBoard into some log directories that you have, and then you view this here. Now, from what I can tell, I haven't been able to get this to work within the Kaggle environment. So I'm trying to set this up so that you'll also be able to run this in Colab. But I'm having to move all or a sample of the data over to Colab too. And right now the data, this is just a huge data set, and it's been taking over 12 hours just to download the data, and it keeps failing because of some internet issues. So I'll try to set this up, but right now I'm not able to get TensorBoard working right now. But I'll try to post an update later on this week on this. But certainly you should read a little bit about how TensorBoard works and how it is set up, because it can be very useful for visualization. So, okay, so we're training our model. Now, let's say we have our weights. We've just spent, 4 hours or 20 hours training this network here, and we want to save our weights so we don't have to do this again. Now this isn't that useful often with Kaggle, because Kaggle sometimes competitions have some requirements as far as retraining and bringing in saved data and stuff like that. But for your own research, we do this frequently. So we can save our weights and load in our weights. And again, actually, this is just before the callbacks, I think. There's a section on saving and restoring our model. So if we create a model, we can then save the model. So you can save the model. This saves the model structure and generally the weights. You can also just save the weights separately here, and then you can load in the weights. So I often have this code, the code for loading the weights, commented out at the beginning of my notebooks, and then and then I have this code at the end of my notebooks, or I'm doing a callback that is saving the best weights out there. And then, so I will have trained this note for a long time, save the structure and the weights, and then next time I run this, I will load in the weights again, so then I don't have to retrain the network. So again, I often stick this code right here up at the beginning of the notebook and do it. And again, I've got it commented out here. It does work, but again, it just shows you how this works. But again, I don't need to do it here in this Kaggle environment. So. Okay, let's try to run this a little. So again, these are large networks that use up a fair amount of memory just loading in these networks. So this is the, which I think I'm using the dense network here, which is a pre-trained model, but it has 7 million parameters here that it's working on and weights, and so it takes a while, and some of the other ones work well. So it will take a long time. Now I have GPU enabled, so training is actually quite fast for this that we'll see. Now one thing I will see now is my accuracy is actually going up really fast from 23% all the way up to 99% here. But my valuation accuracy is actually quite low. Is only about 24%, 23%, and is actually not increasing much. And that one of the reasons, I mean, there's a number of reasons here, and this is what I'm basically doing is my model is just memorizing the 500 images I'm training on, and not generalizing. So we call this overfitting here. And so if I look at a picture of the results here, let's go back down here. I can see my model accuracy increased a lot, but again, my validation accuracy. I'm very good at predicting results for images I've seen, I've trained on, but I'm horrible or very poor at predicting results for images I haven't seen before. And part of that is that I'm only looking at 500 sample images of the 10,000 images I've had. So I certainly want to change that. And if you remember up above here, where was that? Where we're loading in these images here, I'm only loading in and working with 5. So I want to change that. But again, I wanted to show this here. I mean, when you run it that way, it takes a long time to load in the images, and then it takes a long time to train too. So right now, training works, and I can go through this, but I'm only training for 20 epochs. Also, eventually, I might want to change that. Okay, so that's the basic setup for this network. Now, one thing is a little different for this. Is that I'm going to have you do your mini project on this same thing. So I have a couple mini project questions here to have you build on this. So our mini project is tied to the same notebook because it's kind of large and complicated. See if you can try this out and see how it works.